It's absolutely wild to think about the unseen magic that makes modern computers so incredibly fast. Welcome to today's Explainer. We're going to dive straight into some fascinating concepts from Chapter 28, Appendix G of our source text, and we're specifically zeroing in on the inner workings of CPU instruction pipelines. Just imagine an extremely busy airport runway. If planes just decided to take off and land whenever they felt like it, yeah, you'd have an absolute disaster on your hands. Well, your computer's processor is exactly the same way. We're going to look at the ingenious algorithms that act as the ultimate air traffic controllers, literally keeping billions of instructions flying through your processor every single second, completely crash-free. To unpack this hyperactive factory, here's our roadmap for today. We'll hit the processor traffic jam, preventing pipeline collisions, the magic of reorder buffers, Tomasulo's out-of-order genius, and finally, keeping score of instructions. Let's get into it. Section 1, the processor traffic jam. So we have to start with the absolute nightmare scenario for any processor, the traffic jam. Before we can even think about fixing the problem, we need to name our biggest enemy. In computer architecture, this is called a structural hazard. Basically, if two or more instructions try to use the exact same shared pipeline resource at the exact same clock cycle, bam, you get a crash on your processor's assembly line. Thinking about a three-stage dynamic pipeline beautifully illustrates why this gets so tricky. Unlike a simple straight-line process, a dynamic pipeline can do different things at different times using feed-forward and feedback loops. It's complex. If you feed instructions into this kind of loop too fast, well, you can easily see how that would cause a disastrous pileup inside the processor. Section 2, preventing pipeline collisions. Okay, so how do we actually avoid these structural crashes while still feeding instructions in as fast as humanly possible? Enter the collision vector. Think of this as the master traffic schedule for our processor. It's essentially a sequence of bits telling us exactly how many clock cycles we absolutely must wait before sending in the next instruction. See a 1 bit at a certain position? That means starting an instruction right then will cause a collision. It is a strictly forbidden latency. Now, to actually find that vector, we use a reservation table. Think of the x's as our occupied functional units over time. By literally sliding a copy of the table to the right over itself, we can visually spot when those x's overlap. If they overlap at, say, a 2-cycle or 4-cycle shift, we know for a fact that waiting 2 or 4 cycles will cause a crash. And just like that, we've got our binary collision vector. So, how does this build into an automated system? Well, computer engineers use this brilliant 4-step math procedure to figure out when we can safely initiate new processes, all without having to memorize the entire schedule. By continuously shifting the collision vector and using a bitwise OR operation with the initial vector, which is basically just overlaying our new schedule right on top of our old one, the system constantly generates these safe new states. And all that math results in a state transition diagram. It plots out every single one of those calculated permissible shifts. By following the pathways between these state nodes, the CPU maps out a latency cycle. That's a repeating loop of instructions that can run indefinitely without ever causing a structural crash. It literally guarantees safe, continuous throughput. Pretty cool, right? Now here is something truly counterintuitive. Fun fact, introducing a deliberate 1-cycle delay into the pipeline can actually increase the overall average processing speed. No way, right? But by intelligently calculating these states, sometimes slowing down one specific step creates a new, faster loop called a greedy cycle. It squeezes out an extra burst of overall performance for your software. It just proves that sometimes you literally have to slow down to speed up. Moving on to Section 3, the magic of reorder buffers. All right, now let's talk about completely cheating the waiting line. I mean, why wait in a linear line if an instruction has all its data and is ready to go right now? Asking that question led to a massive paradigm shift in computer architecture. We moved from strict in-order completion, where everyone just politely waits their turn, to out-of-order completion. This is where instructions finish whenever they possibly can, but are cleverly committed to the system in their original program order. Historically, to keep everything organized, processors used a result shift register. This enforced a super strict rule. No instruction was issued if it would finish before a logically preceding one. So if an earlier instruction took longer, absolutely everything behind it just had to stall and wait. Talk about a bottleneck. But to execute out of order, modern superscalar processors use something called a reorder buffer. This is a circular storage unit that catches all those chaotic, out-of-order completed results. It holds them temporarily and then, this is the magic part, neatly commits them to the main register file in the perfect, logically correct program order. It's kind of like having a chaotic, busy kitchen, where all the dishes are cooked at completely different times, but a master waiter ensures they are served to your table in the exact right sequence. Section 4. Tomasulo's out-of-order genius. Let's dive into one of the most legendary systems to ever manage this out-of-order chaos, Tomasulo's algorithm. Originally developed for the IBM 360/91 floating point unit, Tomasulo's breaks the instruction flow into 4 highly efficient phases: fetch, issue, execute, and write back. But the real magic? That happens right between the issue and execute phases. Notice the reservation stations attached to the adder and the multiplier. Think of those as the holding pens. When an instruction is issued, it goes right there to wait for its data. It buffers the data locally, right at the functional unit, and that completely eliminates the need to constantly read from the main register file. It's a huge time saver. Tomasulo brought some truly brilliant innovations to the table. By dynamically tracking when operands broadcast over what's called the common data bus, and by renaming registers on the fly to remove artificial dependencies, this algorithm actually distributes the control logic right down to the reservation stations themselves. So, the absolutely crucial takeaway here is that Tomasulo's genius dynamically eliminates those nasty data hazards. We're talking read after write, write after read, and crucially, write after write hazards. It makes sure only the last instruction actually writes to the main registers. That keeps your system data perfectly safe while executing operations at absolute blazing speeds. And our final section, number 5, keeping score of instructions. Finally, let's look at another classic way to manage all this execution chaos. Pioneered in the famous CDC 6600 supercomputer, scoreboarding takes a very different approach. It acts as a strict, centralized traffic cop. The scoreboard constantly monitors 2 tables, one tracking functional units and another tracking registers. If an instruction might cause a resource conflict or overwrite data too early, the scoreboard simply throws up a red light and stalls the instruction from issuing until the path is totally clear. So, if we compare the two, Tomasulo's algorithm distributes control and cleverly renames registers to completely bypass stalls. Scoreboarding, on the other hand, takes a centralized, slightly more rigid approach by just pausing the issuance until the runway is safe. Both are total masterclasses in solving the exact same pipeline bottleneck, just using vastly different philosophies. As we wrap up this explainer, it's just wild to think about. These brilliant algorithms, reorder buffers, Tomasulo's, scoreboarding, they were developed for the giant room-sized supercomputers of the 1960s. Yet they are the very foundation of the unseen magic powering the blistering speed of the smartphone in your pocket today. It really leaves us to wonder, what will the pipeline algorithms of tomorrow look like? Thanks for learning with me today, and keep exploring.